Hello again. This video is about a very famous irrational number, phi. And this is the symbol for phi. This is the value of phi, and it is irrational. So if we were to input this in a calculator, we would get a never-ending, non-repeating decimal, which could never be written as a fraction. And this is another version, 1 plus 1 over phi. I'm also going to use the famous Fibonacci sequence to show you how it can be used to approach this irrational number with a construction that we'll see in a little bit. So this is one of our big questions. How is this sequence related to this irrational number? We'll help answer the relationship between the Fibonacci sequence and the irrational number phi by looking at a picture, which is very similar to the rectangle constructed right here. So let's talk about this. What we have here is the golden rectangle, which has something called the golden ratio if comparing the length and the width. So here's how we construct this golden rectangle. We start with any square. So the blue segments are a by a, and this could be any real number measurement. From the midpoint of one side of this yellow square, we will draw a segment connecting this midpoint to one of the vertices not used in the construction of side A. There will then be an arc drawn. So that's what this point is showing, is that if we drew this arc until we intersect the line that would coincide with this side we started with, we will introduce another distance, b. And a plus b makes up one dimension of this golden rectangle. A makes up the other dimension. Now there's a very important and special relationship between these two measures, a and b. Now one thing to notice is a does not have to be any particular measure. I could lengthen this or shorten it. It could really be an infinite number, and as long as it's a positive measurement and b has the same proportion according to construction technique that we used to get this golden rectangle. So let's look at the relationship between a and b now. A to b forms the golden ratio, which is phi to 1, when a plus b compared to a equals a compared to b. And we can see that I did actually input these measures, and you can see that they are variable. Right? My a and b are both changing as I drag this point. They're getting larger and larger and larger, but the ratio comparing the sum of a plus b to a and the ratio comparing a to b is exactly the same ratio. This is one of the cool things and why this number phi is special. Now let's look at the use of the Fibonacci sequence. And I'm using them as a tool for a construction of a rectangle. The very first square of this construction is the one I'm tracing right here. And this one has 1 by 1 dimension. So there's our first term in the Fibonacci sequence 1. Then adjacent is our next 1 by 1. Adjacent to those two, we have our next Fibonacci term. We have a 2 by 2 square. So we're going 1, 1, 2. This next square has a dimension of 3 by 3. 1, 1, 2, 3. And here is the continuation of the Fibonacci sequence. And what it is a spiraling collection of squares. The next square always has the dimension of the next Fibonacci number. So now we would be at dimension 8. 8 and 5 is 13. 13 and 8 is 21. And we could continue this infinitely. And really that's the idea behind the relationship of the Fibonacci sequence and the golden ratio. Now I'm going to show you something else here. If I constructed circles, first circle with radius 1, and then a circle with radius 2, and then 3, and then 5, and then 8. Those circles, I knew where to put the center point. If we took 1/4 of each circle, we get something called the golden spiral. So let's hide the circles and just look at that spiral. A good question would be, at what point would this, let's say I wanted to shrink this down, shrink it, and each time I needed to add more squares and increase it, I could keep shrinking it and keep adding squares. When would this become the golden rectangle? Here's another way of looking at that previous page where we had the Fibonacci squares arranged, making a rectangle which is approaching the golden rectangle. If I take the next largest Fibonacci term and divide by the previous, so 2 divided by 1, 3 divided by 2, 5 divided by 3, 8 divided by 5, and so on. My numerator is always the next largest Fibonacci number divided by the previous Fibonacci number. And if you look at the decimal approximations of these ratios, there comes a point where, if rounded to 5 decimal places, we get the same value over and over and over. And this is a usable approximation of phi, 1.61803. We would actually get to the number phi when our denominator was f sub infinity, so that would be the infinite Fibonacci term, and our numerator would have to be one more. So is it possible to get to infinity? And if so, can we then add one more? So again, in this video I wanted to help make a connection between the ideas of the golden ratio, the golden rectangle, and the golden spiral. And again, here are the values of phi. Thanks for watching.